Good afternoon, everybody. Thank you for joining us for Clear Signals 102. I'm Catherine. I'll be helping host today. We're just going to give a couple more minutes for a few more people to join us, and then we will get started. All right, I think we're about ready to get started there. So again, thank you for joining us for Clear Signals 102. So you would have attended Clear Signals 101 and gotten kind of our introduction to ATSPMs and using those to improve your networks. So now in 102, we're going to dig further into how to really dig into those reports and start making active and proactive changes to your network. So we do have a question section here, so feel free to put any questions you have in there. We will go over those at the end of the session and get those answered for you. I'm also in our chat going to put a post to our quiz. So after you complete the webinar today, you can complete the quiz, and just like with 101, you'll receive a certificate of completion for that as well. So I'll put that in the chat, and you'll also be emailed that following the webinar. All right, so we have both Sajad and Olivia with us today. They're resident traffic engineers, and they're going to walk you through Clear Signals 102.
Okay, hi everyone. This is Olivia. I'm going to be starting us off today. Sajad, if you could go to the next slide, that would be great. So the course breakdown for today, this is the slide that you would have seen in Clear Signals 101. We've just kind of updated to what we'll be covering today under Clear Signals 102. So I will be kind of doing a brief overview of what we went over in Clear Signals 101, so understanding signal performance data, and then a couple of traffic engineering concepts. And then Sajad will be taking you through a corridor performance assessment, conducting before and after studies, and doing a few more corridor and intersection assessment examples. Next, thank you. Again, at the end of this course, you should be able to describe what signal performance measures are, understand what the charts are showing you, assess the performance of both a corridor and individual intersection against objectives, and ultimately provide recommendations in addressing intersection and corridor level performance. Thanks. And then, yeah, to begin with, I'll just do a quick review of Clear Signals 101. So ATSPM's automated traffic signal performance measures, signal performance data. So the idea behind ATSPMs was at Purdue University, along with some agency partners, we're trying to find a way to leverage existing infrastructure, things like detectors, controller, phasing information, to measure the performance of roadways from the perspective of road users. And then the goal of collecting that data would then be to ultimately use that data to point out exactly where issues are occurring at an intersection level, at a corridor level, why they are occurring, and what we might be able to do to fix those issues. So this is a bit different to what we kind of traditionally do with conventional traffic engineering methods, where we're doing a lot of demand measurement through things like turning movement counts, collecting that sort of data, and then using that information along with a lot of assumptions to create and calibrate traffic models, which are then kind of modeling what performance might look like. Whereas with ATSPMs, we're actually measuring that performance directly. So obviously modeling, sorry, Sajad, could you go back for 2 seconds? Yeah, so modeling is still going to be important in traffic engineering, but with this ATSPM data, models will be now kind of equipped with more high quality, up-to-date data, which will result in more realistic and representative models. So then just kind of to reiterate the difference between the conventional traffic engineering approach versus kind of the new approach, ATSPM approach. Obviously, this is very simplified, but traditionally, like I said, we would measure demand through things like turning movement counts. We would then put that into a traffic model, evaluate that traffic model, and then implement some improvements or optimizations, and then kind of just leave it at that without any kind of feedback loop. Whereas with the new approach, the ATSPM approach, we are measuring performance and then evaluating that performance kind of like against some objectives that we might have set for ourselves. And then if we're not reaching those objectives, then we look at ways to improve and optimize. And once we have implemented those improvements, because we're continuously collecting that data and continuing to monitor, we can check back in with how we're doing. So we can check again, measure that performance. Are we meeting our objectives now? If yes, then we're good. We can keep checking in and keep looking back at that feedback loop. So what we're advocating for here is healthy signal as intersections and corridors. So the idea is that agencies will set themselves some performance objectives, and they can leverage ATSPM data to understand and evaluate if they are achieving those objectives. So obviously healthy, quote unquote healthy, is going to mean different things to different agencies. Even intersection to intersection, you can set yourself different objectives. But once an agency has set an objective, so for example, along a corridor, say an agency is trying to maximize throughput, they can then look at the ATSPM data, evaluate across a couple of metrics, say arrivals on green, different metrics like that, and understand if they're achieving their objective. And if they're not, then the data can often inform them of what changes they might make to achieve those objectives. And then, sorry, Sajad, just a last point on that slide. The data-driven approach can also address road user complaints. So if you do receive a complaint from a road user, because we are continuously measuring and continuously checking that data, if they give you a bit of information, say they experience long delays at an intersection at a certain time of day, you can go back into that data and validate if that user complaint was valid. Next, thanks. And then we have kind of come up with 4 levels of evaluation to understand if we have achieved our objectives. So those are those 4 levels are maintenance, operations, optimization, and safety. So basically they all go hand in hand. You start on the maintenance end. So a simple example of that would be, are your detectors functioning? If you have a detector that is stuck on, obviously, regardless of what's going on with your timing plans, that's going to have a huge impact on performance. So that needs to be addressed before anything else can be addressed. So once you address your maintenance issues, then you can move on to operation and your operational issues. And these are kind of qualified as prerequisites for optimized plans to work. So for example, Are you experiencing phase termination issues at an intersection? If you are, what is causing that issue? Is it passage time? Is your passage time too long or too short? Have you checked your minimum green times? Are they too long? Are they too short? So addressing issues like that. Once we've addressed maintenance and operation, then we can move on to optimization. So looking at optimizing things like splits, cycles, offsets, and time of day plans. And then ultimately, once we've gone over maintenance, operation, and optimization, that will lead to optimized operation, efficient operation, and ultimately safe operation at intersections and along corridors. And then importantly, once you have achieved that objective that you set yourself and you are experiencing a healthy signalized intersection and corridor, again, because of the continuous nature of the data, we can keep checking back in to see, are we maintaining that health? Are we maintaining those objectives? Rather than kind of traditionally where we might perform a major signal retiming and then have no way of really checking back in. With ATSPMs, we can continuously monitor, and if there's a little change in travel demand, or if there's a detector failure, we can fix those things right away, where we kind of eliminate the need to do major changes. Oh, there we go. So just a review of where our ATSPM data come from. So we have three kind of areas where our data comes from. So we have our signal status from our controller. So that is being read directly from the controller, and that is giving us things like phase intervals, timing plans, phase termination, and is providing the information for our time space diagram. So just getting directly the red, yellow, and green times from the controller. The second source of data is our detector activations. So again, that could be stop bar detection, or it could be advanced detection, using that to collect information about volumes as well as pedestrian button usage. And then if we combine those two sources of data, we have numerous graphs that we create from those two sources, which include split failures, split trend, occupancy ratio, Purdue coordination diagram, which gives us kind of platoon information and arrivals on green. Then we have our pedestrian delay, and we have our yellow and red light behavior, which is ultimately our safety metrics, so red light runners and pedestrian compliance. And then lastly, we have our third source of data, which is Wi-Fi MAC addresses. This covers point-to-point travel time and speed, both of which allow us to produce our congestion scan, our travel time index, and our travel time reliability. Next. Okay, so this is just a high-level overview of the numerous signal performance measures that we provide in our Insights tab within Traffic Link. I am just going to go through a couple from a corridor level. Yep, next please. Yep, and so the first one I'll go through is the corridor congestion scan. Very important in our corridor level evaluations. The corridor congestion scan reports travel time at different times of day in relation to distance along a corridor. So what you require, this doesn't require detection, requires 2 smart links, and is using travel time from one intersection to the next. So within this chart, you can see we are showing 2 directions of travel. So for example, on the left here, this could be eastbound, and then on the right here, this could be westbound. And we're showing it along a corridor that has 1, 2, 3, 4, 5 intersections. So we have 4 different parts of the corridor. At the bottom here, we have our time scale going from midnight to midnight across one day. And each band here represents a 15-minute median travel time index. So what the travel time index is measuring is the average travel time over the free flow travel time. Free flow travel time we consider to often occur in the early morning and late evening. That would be when travel time vehicles are moving through the corridor relatively easily with minimal delay, not a lot of congestion, so they're moving freely, hence free flow travel time. So at the top here, we have our scale, which is colored. So we're showing that a travel time of index of 1, which would be free flow travel time, is a dark blue color. And then we can see kind of as we move through the day, we have some bands that are yellow, which is moving into the 2 to 3 travel time index. So here we have indicated that yellow is 2.7 travel time index. So for example, if we look in at this direction between these two intersections, we see that around 3 p.m. We have a travel time index of 2.7. So this would indicate that across that 15-minute period in between those two intersections, we have a travel time that is about 2.7 times higher than free flow travel time. So just a good way of identifying bottlenecks within your corridor. We can also change a few things at the top of the chart. So we can look at things like travel time exemption index, which is the ratio of the median travel time to the historic date range. So that would be 4 weeks into the past. So comparing the date range that you've selected to the previous 4 weeks. And you can also on the right there indicate planning index, change to planning index, sorry, which is the 95th percentile speed over the free flow speed. And this is just showing your reliability in travel time. So is travel time pretty consistent, or do we have kind of varying travel times? Next, please. And then lastly for me, one last chart. This is our time-space diagram, pretty commonly known in the traffic engineering world. We are getting our time-space diagram information directly from the controller, reading that phasing data directly from the controller. So in this diagram, we can see across the top, we have our time from 9 a.m. to 9:05. This is configurable and can be a 5-minute period, a 10-minute period, or a 15-minute period. And then on the left here, we can see our intersections. So in this corridor, we have 4 intersections, 1, 2, 3, 4. And then on the right here, we have this arrow that indicates that going down the page is westbound. So these blue bands are traveling westbound through the corridor from top to bottom, and these purple bands are traveling eastbound from the bottom of the page to the top. We can see that these bands are varying widths and kind of happening at random, not really consistently. So this is indicating that we generally have poor coordination along this corridor. And then that is it for me. I will turn it over to Sajad.
Okay, thank you so much, Olivia, for that background. Hi everyone, this is Sajad. Thank you again for taking the time today. We're going to go over a variety of examples here, just to showcase the power of using ATSPMs. And for this purpose, I'm going to structure the examples around a really handy feature, intersection health, that we've recently released in our Miovision traffic link software. So I'm going to start off with a bit of motivation, and it's coming from yourself, right? It's coming from users, coming from the industry, of why we sort of decided to take this route and how this is helping sort of move forward the usage of ATSPMs. And then after this, we'll, with a brief introduction here, we'll dive into some examples, practical examples of how these problems can be identified and addressed using the data. So in a pretty recent webinar that we had, we asked hundreds of the attendees that we had, like, what is the biggest challenge you have in using ATSPM data? And as you can see here, around 80% of the answers were either about the difficulty in interpreting the data, not enough training, as well as requiring too much time to dig into insights. I think it's a very relevant problem, because sometimes you have the problem of not enough data, and then you have the problem of too much data. So once you have access to the insights, you can imagine there's like 20 different insights multiplied by hundreds of intersections. It's going to be a lot of data for someone to actually dive into and dig into and be able to identify issues, and doing that on a regular cadence is an extremely difficult task. So it was interesting, sort of a snippet from a recent document on evaluating the benefits and costs of automated traffic signal performance measures from FHWA, and one of the issues that MCDOT had identified as room for improvement was the need to orient performance measures towards an actual task. So how can we take that data and all this data performance measures that Olivia walked you through? How can we now turn that into an actual task for a user to take that and actually action on it? So for this purpose, we did an evaluation of more than 200 intersections, and this was an evaluation that we did over 3 months of data. And what we identified was quite interesting, where quite a significant number of intersections were experiencing some sort of traffic performance issues. So we sort of categorized those types of problems that we were seeing, and what we identified was that there were 3 main problems that a lot of intersections and corridors suffer from, that don't need to suffer from, and there's really room for improving that according to the agency's objectives. And around 35% were experiencing suboptimal green split. Around 38% of the intersections were having phase termination issues. Around 41% were having some kind of issue related to poor coordination in hours throughout the day that were actually coordinated, and that shouldn't have happened. So this motivated us for intersection health. Okay, if these 3 problems are very common across a lot of the intersections, why don't we sort of create? Why don't we allow the user to sort of be able to see those problems automatically, as opposed to digging into the data every single intersection, at least opening up multiple graphs and being able to interpret that, but being able to translate that data into an actual problem, right? So we targeted these 3 problems: phase termination issues, green split issues, and poor coordination, which the examples that I'm going to go through are around these 3 problems. Where on a regular cadence, the engines behind this, the data automatically crunches the data and identifies these 3 issues and surfaces those. Just to show you sort of an example of that, would be a case like this. So this is one of the cities, and the system automatically, as you could see, the intersections that have an exclamation mark, those are the intersections that we have identified as having either of these 3 problems that we're talking about. And by clicking on that intersection, takes you to the actual intersection, the movement's there, and actually highlights the movement that is suffering, and it's highlighting what kind of statistics, highlighting some of the statistics that are happening. So for example, at the southbound left turn movement, 38% of the cycles are experiencing the SF category, or what's called a split failure. Tells you the time that's happening, and if there are multiple problems, it'll show you that. There's still the performance measures to be able to sort of dig in further, or if someone's interested to be able to know more, but there's sort of, this is a step where we've taken towards turning to the first step, I would say, and more to come, in order to turn that data into an actual insight, and not to just provide raw data. So around these sort of 3 problems that we talked about, first one, green split issue, I'm just going to go over a few examples of what these problems are, and some of the problems that we've seen in the field, and some potential solutions for those. So a bit of a refresher on this split trend or split failure graph. So one of the, as Olivia mentioned, one of the pieces of infrastructure that ATSPMs take advantage of are stop bar detector information. So there's stop bar detector information, and we have the signal status information, and one of the performance measures that Purdue has created is what's called the split failure graph. And by using the stop bar detector occupancy during the green time, and during the first 5 seconds of red, actually categorizes each cycle for each movement in terms of where they are on that GOR ROR graph, and classifies that cycle into one of the categories that you can see on the bottom of this graph here. So imagine a case like this on the left where there's a queue of vehicles, they get a green light, they're passing through, and then it turns red. But there's still vehicles that have not been able to clear the queue. That would be a case where you have high green occupancy ratio, you have high red occupancy ratio during the first 5 seconds, and that is classified as a split failure. So you could imagine that for each movement, for each cycle, we're identifying that. And one of the ways that we visualize this information is through what we call the split trend graph, where across a 24-hour duration, we take the number of cycles in each 15-minute duration that is experiencing that specific class of that category of performance, and we visualize it. So using a stacked bar chart format. So you can imagine, just by looking at this, it's very clear that this movement from around 4 p.m. to, it seems like 7 p.m. is experiencing a significant spike in the number of split failures that are happening. And then this graph allows the user to be able to not only look at one day, but look at trends as well too. So when you select this graph and you look at it for multiple weeks or days, it aggregates that, and you can actually see if there's an issue that's happening as a trend or not. So this is sort of a refresher on this issue. So you can imagine something like this. The intersection health would automatically identify that the eastbound left turn movement in this case is experiencing a significant number of split failures are happening during the morning peak and during the afternoon peak, whereas the opposing movement is having spare capacity. So it's not just about identifying sort of it's not just about setting a threshold and say, okay, split failures were higher than 20%, alert us. It's about identifying opportunities within the context of the ring barrier diagram. So identifying what are the critical movements in the ring barrier diagram, how are each of those performing, and is there an opportunity to sort of be able to tweak some of them to be able to address the issue. So you could imagine here, we have identified a green split issue here for the eastbound left turn movement. AM and PM are having a spike in the number of split failures, whereas the westbound through movement, which is the opposing movement, does not have that issue. It actually has quite a bit of blue and green, which is more like spare capacity and more in the okay zone. So there's a lot of spare capacity. This movement, I have to explain that this is only protected left turn. That's why they wouldn't have sort of the capacity in the permitted portion in order to pass through. If they had the capacity during the permitted portion, there would have been a graph for that as well, and it's possible to assess against that as well. So that's something that intersection health also does. It assesses the capacity that is provided during the permissive portion as well. So in a case like this, we can see that through the graphs again. So this is where you sort of need to dig into the data a little bit and see, okay, what's happening? Well, the bottom chart here is what's called the phase interval chart. For the ones who can't remember, for each cycle, it's showing the amount of green that's being allocated to all different movements. For this specific movement, as you can see, the eastbound left turn movement, in a lot of cases during the AM and PM, is actually maxing out. So it's reaching that maximum 30 seconds that it's being allocated to. And clearly, one of the solutions to be able to address this problem, that this is how this problem was addressed, was to add just a few seconds to the eastbound left, take that away from the westbound through, and allow the eastbound left to use that. If it doesn't need it, well, it will terminate and it will reallocate that green time automatically to the westbound through, because that's how coordination works. So this is a clear example of how a green split issue, when identified through intersection health, can be addressed. Another problem that we talked about was phase termination. This is another common issue that we've seen in a lot of intersections, and it's actually quite common. And as Olivia mentioned, there could be multiple reasons behind phase termination issues. So phase termination issues are cases where a minor movement is supposed to terminate when there is no demand, either vehicular demand or pedestrian demand, but it's not doing that. And there could be a variety of reasons behind why that's happening. Really depends on the context. So this is an interesting example of that happening. And I just want to explain sort of how that was identified and how it was addressed. So in a case like this, there's an intersection here near a school on a major sort of highway, and our equipment was installed on that. And immediately after sort of a few weeks of the equipment being out there, the data starts coming, right? Data starts coming, you can start to identify some of the trends that are happening out there. Specific to phase termination issue, which again is one of those issues where intersection health automatically identifies now, this would be a case where that would identify this happening. So what we were seeing was that at this intersection, the northbound left turn movement, again, it's a movement that is protected only. And what was happening was that there, as the northbound left turn was a lagging left, it would be serviced, and then it would just remain in green because the concurrent northbound through movement would continue to extend the phase. So this is causing sort of extra delay for the southbound through vehicles. And sometimes this could be quite high. So as you can see here, at around the 15-second up until the 36-second, the northbound left is just staying in green, and the southbound through is being delayed, whereas no one's there. You might have even experienced this when you're driving. Sometimes you feel like there's no one on the opposing movement. Why aren't I able to go? That's a phase termination issue that traffic engineers are well aware of the impacts. So you can see here that the way that this was identified was, again, the split trend graph, one of the best graphs I think that could really help assess the performance of an intersection from various perspectives. And on one of the areas, apart from green split, is the phase termination issue. So again, as you can see, northbound left turn movement, it's a minor movement, it's a minor left turn on, it's a left turn on the major movement. It needs to be serviced, terminated properly. So a good looking graph in this case would be a graph where you have the split trend graph nice and green, because what that shows is that the vehicles are occupying the stop bar detector more than 80% of the time that's being allocated to them. When there's no one there, it terminates and it's done. But in this case, you can see there's a lot of blue or spare capacity that was happening. So this sort of shows that if there's video available, that's actually better, because you can actually take a look at the video and verify that that is in fact the case. So after this, so the city engineer there decided to put in a very interesting solution in order to address this problem of that northbound left turn not terminating properly, and that was to allow the southbound through movement to be reserviced within the same cycle. So that southbound through movement that we talked about, I can show an example here, a video of that actually occurring. As you can see, that northbound left vehicle is waiting for its signal. It is a lagging left turn. The vehicles that are going concurrent are northbound through. As you can see, northbound left gets its green time. There was one vehicle, it passes through. And then what's happening here, this is after the fix was put in place. So had the fix not been put in place, these southbound through vehicles would have needed to wait another complete cycle in order to pass through. So very efficiently, it's reservicing that. And then the impact can be assessed through multiple graphs. So one is the split trend graph again, so the same chart that was used to be able to identify the problem, or through intersection health that automatically shows that. and then being able to go back to the graph and say, okay, yeah, there's a lot more green. There's a lot more cases where the left turn is used efficiently, and it's not creating delay or unused green time on the northbound left turn movement. Another chart that can be used to be able to assess the impact of this is green allocation. So green allocation technically just shows you the percentage of green time that's being allocated to a specific movement. So in a case like this, well, in our software, you can sort of right off the bat sort of use these sliders to be able to assess the impact immediately. So in a case like this, from around 2 p.m. to 7 p.m., there was a significant increase in the percentage of green time the southbound through movement is now getting. 11% more green time. That's 40 minutes of extra green time that's being unlocked for that southbound through movement over 6 hours. So per day, 40 minutes, that's a lot. This is, so it might seem a phase termination issue. Yeah, it might seem like a simple problem that might not be very impactful, but you can see how a simple fix like this, when it's put in place and solutioned properly, it can unlock an extra 40 minutes for that southbound through movement. So simple problem, but very, very, very impactful. Another case is, as I said, poor progression is another issue that we identify through intersection health. So a case like this, for example, this was a major corridor sort of connecting the downtown core of a city to sort of the suburbs. It's a pretty important corridor there, and the traffic along this corridor was extremely directional. So during the morning, southbound was extremely busy, and during the PM peak, it was northbound. So very directional traffic, and there was a lot of complaints around long delays and long queues along this corridor. So one of the first steps in assessing sort of a corridor and seeing what's going on, in my opinion, what I found really to be useful, especially at a corridor level, is travel time. So travel time is the thing that really road users experience specifically, and it's a really, really great place to start at. And as Olivia described, this is one of the best sort of charts to be able to use in order to assess the performance of a corridor from a travel time perspective, because it not only shows you sort of the 24-hour duration, but it's also showing you each different section along the corridor, as well as their respective performance or their travel time, their median travel time. So in a case like this, we have northbound on the right side, we have southbound on the left side of this graph, and very easily, just by looking at this, because sometimes even if there's a complaint or anything, it's always good to assess, okay, how bad is the situation? And I think this really speaks to that, and being able to identify, okay, is there a bottleneck? Is this something that's happening consistently along the corridor? What time is it happening? Is it a trend or not? Is it happening on specific days? So there's a lot of information that just can come from this single sort of chart to be able to assess and see, okay, answer all these questions and say, where's the problem? When it's happening? Is it a trend or not? Is there a specific intersection that is the bottleneck? So in a case like this, you can clearly see that during the PM peak along the corridor, this is something that's happening as a trend, not only as a trend, because this is a multiple week chart. But as you could see, it's not just one intersection that is experiencing a significant spike in travel time. It's sort of all the different three sections along the corridor that are experiencing that. So it's not just one bottleneck that needs to be addressed. So as you can see here, the red area, as Olivia explained, so what we're seeing is that travel times are more than 4 or 5 times free flow. So along this corridor, something that should take like 2 or 3 minutes would take 10 minutes, 12 minutes in order to pass through. So assessment at a high level using something like travel time really, really helps, because you can identify the more pressing issues that need to be addressed right off the bat. So the second thing, after you looked into, okay, the performance seemed like PM peak, okay, what's the next natural step? Okay, let's see what the controller is doing during that time. So for that purpose, you can go and look at the phase interval graphs. It's exactly showing you what the controller is doing. No timing plans or anything that's on paper, because a lot of cases they are actually incorrect, or might not be, or the controller might not be doing what's supposed to be doing in the field. So what better than to see what the controller is actually doing in the field? So the phase interval graph, as I said, it's just showing you the cycles. So each of these bars is showing you the cycle. The red part is obviously the red portion of that, and the green is the green portion for each individual movement. So for example, for the northbound direction, which was the major direction here, as you could see during the AM, PM, cycle lengths are variable. This is a sign that this intersection is not coordinated. Although the cycle lengths seem to go up quite high and sometimes even quite consistently high, but these intersections were not coordinated, therefore creating poor progression. And so one of the, again, it really depends on how deep you want to go into it and how you want to use this data. I think it's data super rich to be able to use. One of the really interesting things that can be identified from the data, especially in cases where the intersections are operating in free mode, is the natural cycle length that's happening. So this is an indication of what is so if you're just allowing the demand to determine what the cycle length is, what is the cycle length? And by using this information, it was actually possible to use those natural cycle lengths to determine sort of a percentile of cycle lengths that is happening at each of the intersections during the PM peak, and then being able to use that information to determine the coordination cycle length along the corridor. Another interesting thing that the data was showing was that at some of these intersections, again, due to the free mode operation during the peak hour, very, very short cycle lengths were happening. So they were making some very short interruptions to the major because, again, it was free mode. So whenever there was demand on the minor, as long as it had met the demand on the major, it would terminate and then go to the minor. So lots of interruptions to the major, lots of short interruptions, just because there's like one vehicle on the minor. So that's not a really good operation, especially during the peak time. Maybe during a midday, that would make sense because you want to provide more equality, but in a case like this, not so much. Again, from another perspective, so there's all these different metrics you can use to assess, okay, what is going on? So we just need to understand, okay, what's happening, what's the context that we're working with. Another one, so we looked at travel time, we looked at the phase interval graph, what is the controller doing? We're looking at the time-space diagram. So in time-space diagram, again, this is something that a software like Synchro will never produce for you, right? Because it's uncoordinated, and you can actually see, okay, what is happening from a coordination perspective. So you can see that green bands are non-existent almost. There's lots of sort of green starvation that's happening because downstream intersection is red, upstream intersection is green. It's a case where it's ripe for a lot of green starvation. So although there is demand, although it's a busy corridor, but you just can't use that green time because downstream intersection isn't in sync with the downstream intersection, the upstream intersection with the downstream intersection. So what was the evaluation conclusion? So it's always good to evaluate, okay, what are we doing here? So PM peak, we identified that's the one that's experiencing significant delay. What is the cause of that? It's lack of coordination, as we saw, lots of interruptions, lots of what's it called? The green issues that were happening, and then significant randomness that was happening, and then the free mode operation that was happening during the PM peak. And we saw that there's natural cycle lengths happening, and the corridor itself is actually telling us that it needs that a constant cycle length to work on. So again, using those 90th percentile natural cycle lengths, you can identify what they are. And then ultimately, again, this is where the solutioning comes into play, right? You don't, that reduces the need for the user to go and sort of dig into the data, but to actually work on solutioning. So in a case like this, being able to identify what the percentiles of the natural cycle lengths are, and ultimately the city here decided to go with the 142nd coordinated cycle length along the corridor. There's different directions that one could take from here. In a case like this, when it's uncoordinated, you can use the natural cycle lengths to determine the coordination cycle length. And now, by using a software like Synchro, for example, you do have the splits. You have the splits and the split allocation. You have the coordination cycle length that you've set. So by multiplying the proportion of the split by this coordination cycle length, you can determine what the new splits are. So you have your new splits, you have your cycles, you have the time of day that you want to implement that time of day plan that we saw. You can see that from the congestion scan and the travel time that we saw. We can exactly see what hour throughout the day that needs to happen. And then when you have these three pieces of information, the only remaining piece is really the offsets. And by using some kind of weight or directional weight, you can actually determine what the offsets should be. So in a case like this, the city decided to sort of go with this duration of coordination. So as you could see previously, with the phase interval graph, the cycle lengths were quite variable. That was operating in free mode. Now it's nice and coordinated at a 142nd cycle. The intersections are now aligned, and as you can see, some nice green bands are happening and going northbound. They implemented that from 3 to 6 p.m. and favored the northbound movements because that was the major direction. So if there's some kind of other information along the corridor, so for example, stop bar occupancy, sometimes there might be a camera that provides you with some counts, or there might be advanced detection which provides you with volume information. You can determine that split. So the split, or just assume something, right? Based on your knowledge of the area, you can assume a weight for either the directions, or maybe give more weight to one direction, or just totally align the coordination towards one specific direction. And then once that's done, again, it was implemented. All of that nice data is available to you to be able to assess the impacts. So this is what's really interesting, right? We want to see, okay, was it successful or not? Was it successful in addressing the issues that were happening? Obviously, one of the main sources of something being successful is that complaints go away, right? So definitely nothing beats that. But from a quantification perspective, in order to do sort of an apple-to-apple comparison, traffic volumes, there was actually an increase in volumes. This was because this change happened during the early summer, and then summertime, there's a lot of seasonal traffic that happens along this coast. It was around a 3% increase in volume. There's around 3% increase in volume. And again, you can go back to all of those different charts that we identified the issue and we assessed it, and to be able to do before-after studies. So in a case like this, the northbound through movement, on the left, we have the before condition. As you remember, lots of high travel times that were happening. And then in the after condition, although the demand had increased slightly, you no longer see that significant spike in travel time, significantly reduced what was occurring. Again, we can look at the travel time information on its own. So the bottom sort of dotted line here is indicating the before condition, the after condition, and the top one is showing the before condition. So as you can see, there was a significant spike in travel time that was happening, and that has now been flattened out. And that's the same issue. So again, in our software, you have these tools available to you to immediately assess the impact of the change that was made by comparing the two travel times right off the bat using this nifty tool that we have. There are other impacts as well too. So again, we have report cards available, so you can select the before condition, you select an after condition. So you do 2 weeks before, 2 weeks after, and it actually tells you what kind of changes may have happened along the corridor from different intersections, different movements. Overall, it seemed like even for the minor movements, a lot of split failures had reduced. If there's something that sort of sticks out like this one, there's always a chance to sort of go back to the data and see, okay, what happened here? Is there something that I can do to improve it? And again, all the information is available to be able to convert that into cost savings. Travel time and volume are really the main inputs required in order to do an emission and fuel estimation and savings calculation. So based on total vehicle impacted and travel time savings and emission saving, you can see that an estimated $500,000 savings was happening per year just because of this sort of change that happened in the signal timing. So I'm going to stop here. We have around 10 minutes remaining for your questions. I appreciate everyone attending this webinar. So we're going to go now and answer some of the questions that we've received. Feel free to sort of write in the questions that you have in the chat box, and we'd be happy to answer. And if there's something you don't want to answer here are our emails. Feel free to come into contact with us, and we'll be happy to assist you. So back to you, Catherine, if you want to sort of manage the questions.
Absolutely. So the first question we have here are there any potential safety benefits to the intersection health tool? Have you looked into it?
Excellent question. Really appreciate that comment there. Yeah, for sure. Like right now, we have performance measures that are assessing are providing us with the safety performance of intersections like red light running, like pedestrian compliance, and yeah, this is exactly one of the sort of next steps that we're thinking about, is to add as many problems as possible, right? Like how can you convert those safety metrics into an actual alert, or one of those sort of tickets that you saw in the demo, which now is telling you, yeah, there seems to be a significantly higher number of red light runnings at this movement, for example, and be able to highlight that both at the network level, be able to highlight that at the intersection zone. So this is going to be definitely a theme across all the features that we're going to be releasing from now on. I think it's adding just more charts and graphs to a significant number of charts and graphs, I don't think is the right direction to take. Some of the vendors have decided to take that path, but if we really want people to take advantage of data, really be able to use the information, super important to be able to convert that data into actual information and insight, and that's the direction that we're taking. But yeah, great question.
Awesome. So our next question, for the corridor example, how come the city staff did not even know the signals were not coordinated?
That's a great question. So sometimes that's the thing, right? People change. There's a lot of changes that sometimes happen. Some of the consulting companies are sometimes involved. They knew that it's not coordinated. It's just they didn't have either the resources or being able to like really assess the impact and see like, is coordination even required or not? That was the thing, right? You can sort of guess and say, okay, I'm going to go and coordinate this, but being able to really assess it and be able to understand, yeah, look, this is the hour that you really need coordination. This is the data to support that. And this is how you can go about it and use it. So I think it's more than just not knowing that it's coordinated. It's more about how do you come to the conclusion that now this does require coordination, and how do you go about and implement that.
Awesome. And this is a follow-up, I guess, to that question. So the top signal offset can be shifted to the right to make both directions better. It seems the Main Street runs as split phasing, which is not common. There must be a reason.
Yeah, they were split phasing there due to physical constraints. The thing here is that that's why you sort of it's also important to be able to simulate a little bit as well too, and not just sort of go with the green band. But you're totally right. I think there is an opportunity for them to be able to shift the offset to the right there a little bit for that top intersection and being able to increase the green bands there. There's some considerations for like queuing as well that needs to be taken into account. But yeah, that's a good point. That's yeah, certainly something that they can look into and improve for sure.
Next one. So thanks for the presentation, Sajad and Olivia. Can you please elaborate more on how you use data to identify interdependency of intersections in terms of performance, which might not be on the same corridor necessarily?
Yeah, so that's a good question. I think we need to go back and see how our signal timing is done currently, right? So I think the aim is to at least be as good as that because it requires less amount of data collection and you can sort of do that on demand. In a lot of cases, the current practice of signal retiming is that corridors are looked at into isolation, or there's a number of corridors that are considered together and assessed. There's nothing holding us back from being able to assess use the data to be able to do that. Of course, there's limitations for the ATSPM data to be able to like actually model it and be able to do like a network-wide assessment of that. But let's not forget like how signal timings are done currently. So it's not like if you go and like ask a consulting company to do a signal retiming, they will now consider all the different corridors and everything and look at this from a very network-wide perspective. Usually a specific corridor is selected and it's optimized for that corridor. There are considerations for the major corridors that do interconnect with that, and nothing is really holding us back from being able to use the ATSPM data to do the same. But yeah, I think these are the areas room for improvement for the data, right? To be able to use the data to be able to assess these interdependencies as a network as well. But yeah, great question.
Great. Next one, you talked about the automated detection of problems. How do you do it? Is it a simple linear regression, or are there other intersection-specific details that can affect the escalation of the problem?
So linear regression, I don't know how we would use linear regression, not sure what that means, but the way that we're assessing the problems is just through traffic engineering concepts. So imagine a person has access to this data, and now they want to assess the performance and identify a green split issue or a phase termination issue, for example. What would they do? So they would likely a green split issue. I would go and look at the ring barrier diagram. So what is the sequence of traffic operations here? That's the first thing that I need to understand. Okay, what's the next step? Okay, I need to go and see what the performance of each individual movement is during each sort of specific hour. What's the critical path within the ring barrier diagram during that time? How are different movements performing? And now I can come to the conclusion and say, you know what, there seems to be this movement that sort of sticks out and says that, yeah, this is suffering significantly higher than the other movements. It's not about just identifying the movements that are suffering. It's about identifying the movements that are having a significantly higher amount of congestion, and there is opportunity for them to be able to be addressed if there are some small tweaks to the timing. So the way that we identify the traffic problem is exactly the same way that a traffic engineer would go in and identify the issues. Again, starting off with the phase sequencing, using the ring barrier diagram, all the way to assessing and identifying if there's an opportunity to be able to address it. Obviously, like phase termination issues, that's sort of a different story. Again, it is within the ring barrier diagram as well too, because you could have a minor movement that a north-south minor movement that northbound is busy, but southbound isn't. Does that mean that the southbound is having termination issues? No, because north and south are happening concurrently. So it's extremely important for that to be assessed in the context of the sequence of the phases and to be able to identify. So very short, as a traffic engineer would do it, we identify automatically the same way.
All right, and the last question we have here is, does your system have an optimization function?
At the moment, no, but stay tuned.
All right, perfect. So if there's no more questions, thank you everyone for joining us today. We will be coming out with a Clear Signals 103 in the new year, so we will keep you updated on that, which will kind of conclude this 3-part series. And thank you to Sajad and Olivia for sharing your knowledge with us today. I've put, again, in the chat is the link to the quiz, so you can go and complete that to get your certificate. You'll also be emailed that link after this session. But thank you again, everybody, and have a great rest of your day.